In this video, we will learn how to identify redox reactions and how to balance redox reactions. So let's get started by doing a warm-up problem. In this warm-up problem, I want you to think back to what we learned in Chapter 10 about different patterns of reactions and see if you can identify which of these three reactions are oxidation-reduction reactions, aka redox reactions. Go ahead and pause the video and try to identify which of these three are redox reactions. Okay, let's go over this. So redox reactions were defined in Chapter 10. Redox reactions involve a movement of electrons. So if electrons are moving around, then we're going to see a change in oxidation state. So let's start by identifying oxidation states in each of these equations to see if we can identify which of these are redox reactions. So let's look at this first one. In this first one, we have zinc solid. There is no charge specified on the zinc. It is a pure element. There's nothing bonded to it. So since it's no charge and it's a pure element, its oxidation state must be 0. This one does have a charge, so the copper does have a 2+ oxidation state. It does have a 2+ charge on it. Over on this side, on the product side of the equation, it does not have a charge, and so that's a 0 oxidation state. And on the product side, zinc does have a 2+ oxidation state. So zinc changes from being 0 to 2+, and copper changes from being 2+ to 0. And so since we have things changing oxidation state, this one is a redox. So we know number 1 has to be a redox. That means that we can eliminate answer choice C and answer choice E from our list. So let's work on number 2. In number 2, let's go ahead and erase some of these markings. Okay, in number 2, we have sodium solid, and so that's a 0 oxidation state, no charge specified. Here we have chlorine. It is a molecular chlorine. It's a pure element though, no charge specified, so that's a 0 oxidation state. And on the product side, we have an ionic compound. So ionic compounds are made out of ions. This is our sodium cation and our chlorine anion. Sodium likes to form +1 cations, and chlorine will be 1- ions. That's how they get that noble gas electron configuration. So we do have sodium changing oxidation states and chlorine changing oxidation states. So this one is a redox reaction as well. Now our answer choices do have a 1 and 2 option, but we also see a 1 and, we know that number 2 has to be an option, but we don't know if it's 1 and 2 only or if it's 1, 2, and 3. So we have to check number 3 as well. So let's assign our oxidation states for number 3. Magnesium is alone by itself, pure element, much like the sodium and the zinc, so that's the oxidation state of 0. Oxygen is a diatomic molecule, but it is a pure element. There's no other elements bonded to it. So each of those oxygens has an oxidation state of 0. Now we have magnesium oxide. Oxygen has a common ion charge of -2 in ionic compounds, and magnesium has a common ion charge of +1 in ionic compounds. And so again, we have changes in oxidation states. And so this is a redox reaction. And so our correct answer is D. All of these are redox reactions. All right, let's talk a little bit more about identifying redox reactions. Well, let's first talk about the importance of redox reactions, and then we'll get into how to identify them more. So, redox reactions are all around us. Redox reactions are very important to life processes because photosynthesis is a redox reaction, and so is aerobic respiration, cellular respiration. So every time you breathe, your lungs are doing a redox reaction. You know that you breathe in carbon dioxide gas. No, you don't. You breathe out carbon dioxide gas. You breathe in oxygen gas. And you breathe out carbon dioxide gas. And so in oxygen gas, the oxidation state is 0 for oxygen, and when you breathe out, oxygen has a 2- oxidation state. This is not a balanced redox reaction because I am not including the sugar or the water in this reaction. The carbon can't just appear out of nowhere, but you see the idea. You're changing oxidation state. When you breathe, you are changing oxidation state. Combustion is also a redox reaction. Remember, our combustion pattern of reactions involves reacting with O2, something containing carbon and hydrogen, and your products are always carbon dioxide and water. And so oxygen is a 2- in both carbon dioxide and water, and starts off with a 0 oxidation state in O2. So that one's a redox reaction as well. Batteries also run on redox reactions. Electricity is the movement of electrons. And so batteries have they have chemicals inside that are exchanging electrons. And you make that reaction happen by connecting the two ends together in a circuit. And that allows the electrons to move through your circuit in order to complete the chemical reaction. So we'll get more into batteries and electrochemical cells later in another video. Rusting is another example of redox reactions. Iron can start off as a neutral solid, and then once it forms this orange stuff is Fe2O3. And so you can tell that the oxidation state in each iron is a 3+. So it is changing charge. Also, silver tarnishing is also a redox reaction. The Statue of Liberty is made out of copper. Copper has that color. That's the copper color. Pennies are also copper. All right, like pennies. Well, the outside of a penny anyway. The inside of a penny is zinc. But we don't think of the Statue of Liberty as being the color of a penny. We think the Statue of Liberty is more of a green color because of the redox reactions that have occurred to the copper on the surface. Okay, so let's talk about our reaction patterns that we learned about in Chapter 10 and how we can use those to identify redox reactions. Redox reactions would fall under things that we observe. They're observable. They're usually very violent. They involve color change, light, heat, etc. Violent, rapid. They're usually like pretty intense reactions that involve color changes, light, heat, and whatnot. but that doesn't really help us identify them from a list. So what can help us identify redox reactions from a list of reactions is by looking at our different patterns of reactions. So for instance, double displacement reactions are never redox reactions. So if we see a double displacement reaction on a list of reactions, we know it cannot be a redox reaction. Sometimes combination and decomposition reactions are redox, but not all the time. But single displacement and combustion reactions are always redox reactions. So if we see double displacement reactions, we can rule them out. If we see single replacement or combustion reactions, we know that those have to be redox. And then we can go back and double check any combination or decomposition reactions. You can look back on the warm-up problem for this video, and we had a single displacement reaction and we had 2 combination reactions. And so we had all 3 of them fell under that redox category. All right, just a little bit of review before we get going into balancing redox reactions. Oxidation is the loss of electrons, and so your oxidation state will go up. And by oxidation state increasing, I mean more positive. And then reduction is the gain of electrons. And since electrons are negative, your oxidation state is going to go down. So it's going to become more negative. So you can remember this acronym oil rig or Leo the Lion says grr. I like to remember the changes in oxidation state, and that reduction means that my oxidation state is reduced, as in it's going down. Let's look at each of these reactions and think about which ones are being oxidized or being reduced, if the reactant is being oxidized or reduced. Go ahead and pause the video and try to work that out. Okay, you have ideas? Let's go over this. So if we see electrons on the reactant side, that means we're adding electrons. That's not how you spell electrons. We can also tell by our oxidation state. So adding electrons is reduction. But we can also tell by looking at our oxidation state. Chlorine goes from being a neutral, pure element to being 1 minus ions. And so our oxidation number is going down. And so more negative. And so both ways point us towards reduction. Now on to the next one. Change colors. Okay, so for our next one, we have electrons on the product side. And so that means we lost an electron in this process. This lost an electron. And so that's pointing us towards oxidation. But we can also tell it's oxidation by looking at the charge. These are actually charged ions, so the oxidation state will match the ion charge of 2 plus and 3 plus. And so our oxidation state is getting more positive, and so that's going to be oxidation. Now let's look at these other ones. It says not balanced on them. And so we're going to, they're not balanced, and so we can't look at where the electron is. We have to decide where the electron is. And so here we have sodium going from being a +1 to a 0 oxidation state. And so it's becoming more negative. It's not actually negative yet, but it's becoming more negative. Since it's becoming more negative, this is reduction. And so in order to balance this equation, I would need to add an electron to this. I would need to add 1 electron in order to decrease from +1 to 0. Now we have something that's a 2- oxidation state to something that's a 0 oxidation state. This is becoming more positive. So this last one is oxidation. Now let's think about the electrons. Each oxygen here is going to need to gain 2 electrons. We have a total of 2 oxygens. And so 2 oxygens times 2 electrons would mean 4 electrons in order to balance that. Okay. It's important to remember that oxidation and reduction always happen together. And so the number of electrons lost has to equal the number of electrons gained. So the number of electrons lost has to equal the number of electrons gained. These are what's known as half reactions. They only tell us what is happening on either the oxidation half or the reduction half. And the overall reaction will include both halves together. And you can see the arrow is like our equal sign here. Everything that's on the product side stays on the product side, and everything that's on the reactant side stays on the reactant side. But we can cancel out the electrons because we have that same term on both sides of the equation. So we would report the overall equation without the number of electrons written, but we can be able to tell how many electrons were transferred by looking at the charges. If you're trying to decide states of matter for a reaction, if it's a 0 oxidation state metal, then it's going to be a solid. That refers to like an actual solid piece of metal. Aqueous ions are aqueous, and so they're dissolved in water. Ions are always aqueous, so ions are aqueous. And then the solid would refer to an actual piece of metal, and that has no charge. And so once you dip the strip into the copper solution, then the copper ions actually get plated onto the surface of the metal. And so we have our zinc, our copper, deposited as a solid on the surface of our metal strip. And then my zinc ions are in solution, and we can't see those too well because they're dissolved in solution and they're not colored, but they're there.